We're going to do a pretty quick section on exponential and logarithmic regression. It'll be fairly quick because we've done this with lines and quadratics and all, so it won't be anything too terribly new. An exponential model is just, you've got your set of data and the data looks exponential. So it's either going up exponentially or down. Or it could be logarithmic where it's flattening out a bit. Or it could be a logistic model, which some people also call an S-curve, where it starts out exponential and then kind of flattens off. And that actually makes sense in more cases than an exponential. Example 1 says Kathleen is interested in finding a function that explains the growth of cell phone usage in the United States. She gathers data on the number in millions of U.S. cell phone subscribers from 1985 through 2005. So here's your data. And part A says put that data into your calculator. And so we know how to do that. You go to Stat, Edit, and all this was listed out for you if you need it back in linear regression. So Stat, Edit, put in under L1 and L2 your data. And then it says using the graphing utility, fit an appropriate function to that data. So when you go to Stat and Calc, instead of line reg, you're going to select exp reg, EXP reg for exponential regression. And you'll use y sub 1 and y sub 2, assuming that's where you put your data under. And if you want it to save, remember, and we do want it to save on our graph, so we'll go over to vars, y-vars, and select y sub 1, so it saves in your graph. And then you'll end up with, when you find A and B, we're going to say this is A equals 0.865 times 1.319 is B to the t power. Part C asks us to express that function in the form A naught times e to the kt. So what we're doing is it's still going to be the same function. We're just expressing it in terms of e. The 0.865 is still your A naught in this case. And 1.319 will be e to the natural log of 1.319. So in place of 1.319, we're putting e to the natural log of 1.319. Now, that is legal because e to the natural log would cancel out. It's the same thing. And the reason we do this is just to get that e in there. Now, if you put in your calculator the natural log of 1.319, you get 0.227. And there's your function now in terms of e. Graph the function on the scatter diagram. You can just go over to graph, and it should already be there if you saved it under y sub 1. And then part E says, predict the number of U.S. cell phone subscribers in 2015. So we need T. I know that's still in the past, but yeah. And T will be 2015 minus 1985, which is 31. So we want A of 31. And you could use either function. I'm just went ahead and use the second one. Plug in 31 for T and you should get approximately 4,571 million, which is the same thing as 4.571 billion. Now I want to talk about this for a second. There are approximately 7.5 billion people in the world. So this prediction is saying that 5 years ago, over half the people in the world had cell phones. That is highly unlikely because we're including children, we're including older people, poorer countries, everything. So it's highly unlikely that it would go up that high. So I just want to point out, instead of an exponential, we would want to use a logarithmic, or a logistic, where it would flatten out at some point. Just wanted to point that out. Okay. Example 2, we're going to look at a logarithmic situation. Jody, a meteorologist, is interested in finding a function that explains the relation between the height of a weather balloon and the atmospheric pressure on the balloon. So as you go up into the sky, here the atmospheric pressure rises. It gets greater. And so as this balloon goes up, the atmospheric pressure will rise. So same deal, go over to Stat Edit, put in your data, and then go to Stat Calc and fit this time we're doing an LN reg. That's standing for a natural logarithmic regression. And I'm going to call this H of P for height at the pressure. And A ends up being 45.786. B is 6.903. And then we have the natural log of X, or in this case, we're using P for the pressure. It says draw the logarithmic function on the diagram. So as long as you saved it under y sub 1, you can see it does fit very well. And then predict the height of the weather balloon if the atmospheric pressure is 560 millimeters of mercury. So we're just going to plug in 560 for P. And we get about 2,108 kilometers is how high in the air the balloon will be when the pressure is 560. One more example, we're going to look at a logistic example. The data in this table shows the amount of yeast biomass in a culture after T hours. So we're growing yeast in a petri dish or something like that. And it says, draw a scatter diagram. So there's our scatter diagram. Fit a logistic function to that data. This time you're going to use log reg. So I need to point out here that log reg is not logarithm, it's logistic. LN is logarithmic, okay? LOG is logistic. So make sure you keep that apart there. And so we'll find P of T. So the amount of yeast over time is, and it gives you the top, 663.022. And then we have 1 plus, and then it gives you this number, 71.57 times e to the, and then it gives you this number, negative 0.547. Those three numbers here are all given to you when you do the logistic reg. It says, what is the predicted carrying capacity of the culture? Well, remember the carrying capacity is on top. So it's approximately 663 yeast biomass. So all that will fit in this dish or whatever is 663 of these yeasts. And then predict the population of the culture at 19 hours. So we're just going to plug in 19 for T. And you get about 661.5. And our units are yeast biomass. So pretty close to the carrying capacity at that point. Okay? And so that's our section on exponential, logarithmic, and logistic regression.